Okay, so this is 11, 18, 14, period 6. So we talked about figuring out configuration from location on the periodic table, and you're all really good at that. I think you've got it, which is good, because you'll have to be really fast at it for what's going to come next. But right now, we'll talk kind of specifically about the characteristics of the blocks, and we're going to talk about our two weirdos. So, hydrogen and helium. Okay. These are the original elements. By that I mean, at the point of the Big Bang, in the moments before there were actually atoms of anything, the first atoms to come together would have been hydrogen atoms, because hydrogen is the simplest atom there is. It's a proton and an electron. That's it. You can't get any simpler than that. It's kind of special. So what's the electron configuration for hydrogen? Go ahead and write it. Hydrogen is 1s1. It's just got one electron. Well, where would that put it group-wise? Put it in group 1, which is great. Based on electron configuration, it clearly belongs in group 1. It ends in S1. Here's the problem. Group 1 are a group that have some very defined characteristics. They're solids at room temperature, they're highly reactive, blah, 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 blah. You know, they like to gain, or they like to lose an electron. Hydrogen likes to gain an electron. Hydrogen's a gas at room temperature. Hydrogen doesn't act like group 1. So we put it in group 1 because that's where it belongs based on electron configuration. If you look at this periodic table, you will notice that hydrogen appears in two places. It appears in two places because while on electron configuration it belongs in group 1, it behaves like group 17. The way it acts is a group 17 thing. So it doesn't share the properties of group 1, but that's where we typically put it. So that hydrogen over here in group 17 we kind of ignore typically. Helium is the other one. Now helium, when we say that it's the other original, when you smash 4 hydrogens together, you get a helium. So you smash 2 together, and then you smash 2 more together, and then you smash those together, and you end up with a helium. So it's another one of the originals. Where do we make helium? Where does helium get made in our neighborhood? And I use the term neighborhood loosely. Sun. Yeah, the answer comes up every morning. Get it? Best I can do. So, what's the configuration for helium? One S2, right? So if it ends in an S2, what group would that put it in? Group 2. It's clearly not a group 2 kind of element. So helium behaves like a noble gas. Behaves like a noble gas. We put it in group 18 because of that. If you think about it, so here's our little helium nucleus, and here's helium. This is a Bohr style representation of helium. What is true about helium? It's got a full highest occupied main energy level. The highest main energy level that helium has electrons on is full. It's satisfied. So despite the fact that it doesn't have 8, it's not its fault that it can't hold 8 on that first level. Helium acts like a noble gas. It's totally satisfied. It's non-reactive. It's not looking to gain or lose electrons. So we put it in group 18. If we were characterizing it based solely on its electron configuration, we would have it in group 2. So it's kind of a double standard that we put hydrogen in group 1 and we put helium in group 18. So we put one where it should be based on electron configuration and one where it should be based on characteristics. So actually, maybe Van Brainer's idea is a better one, and put hydrogen in group 17. I'm not going to fight that battle, but anyway, that's something you should be aware of. Talk about the S-block. The S-block is groups 1 and 2, right? And these things are pretty darn reactive. They're reactive enough that we don't typically find them on their own in nature. They form compounds. They're like that needy, whiny friend you have who can never be alone. That's the S-block. Can't be alone. Just can't do it. The number of electrons in their highest occupied level is equal to the group number. Now, what's another word for the number of electrons in the highest occupied level? What's another word for that? Valence. Yeah, those are valence electrons. So for the S-block, valence electrons is equal to group number. So for group 1, how many valence electrons are there? Don't all jump up at once. Just 1. For group 2, how many valence electrons are there? 2. Yeah. Knowing that right off the top of your head, knowing that at 2 a.m. out of a dead sleep becomes really important. Because when we start doing compound formation, you have to immediately know, oh, well, that's oxygen. It's going to gain 2 electrons. Oh, that's sodium. It's going to give up 1 electron. Like you have to be, that has to be just totally second nature. And the first thing that allows you to do that is knowing how many valence electrons something has based on the group it's in. So for group 1, 1 valence electron. Group 2, 2 valence electrons. Okay. They have special names. Group 1 are the alkali metals. Group 2 are the alkali earth metals. I'm going to be honest, I always screw those up. So I can never remember which is which. I don't think it's as important as knowing how they behave. Group 1 is far more reactive than Group 2. We'll see a video possibly today, maybe tomorrow, that demonstrates that. But that's the S-block. Okay, so now we're going to talk about the P-block, and that's this whole side of the periodic table. This is groups 13 through 18, and we very often talk about the P-block and S-block together. We call them the main group elements. So if somebody says, well, it's a main group element, it could be in the S, it could be in the P. It cannot be in the D or F. We'll talk about those in a second. And number of valence electrons on highest occupied level, otherwise known as valence electrons, valence E, is equal to the group number minus 10. Group number minus 10. So if something is in group 17, how many valence electrons has it? 7. If something is in group 14, it has 4. I know, that seems so easy and so stupid. Why would I even ask you that? Because then I'm going to start throwing them all at you mixed up in different ones, and you'll go, let's see, group 13. 13, because it's, no, wait, group 2, negative 9. No. You know, it's just, it's remembering them when they're all shuffled together. I know it's, you know, simplistic, but group 18, our noble gases, are very special friends. They are very stable because they've got a full P. So they're all S2, P6. And having that makes them incredibly stable. We said that there were distinctive properties in the S-block. We don't really talk about properties as a whole in the P-block because they really change from one side of the P-block to the other. They vary tremendously. You know, let's talk more about what's in the P-block. Okay, so still talking about the P-block. This is where all the nonmetals in the whole periodic table exist, and this is mostly the stuff you're made of. One of the biology standards, it used to be very explicit, and I think they've modified it a little bit, was students will understand that all living things are made primarily of 6 elements: carbon, oxygen, nitrogen, hydrogen, phosphorus, and one other one that I can never remember. You know, but this is all P-block stuff. This is all the nonmetals. And the nonmetals, you'll remember, are this sort of little corner up here. It's got all the metalloids. So we'll do the metalloids in some other color. Yeah, the metalloids are that little ziggy-zaggy bit there. It's also got some metals. What it's got that's really important is the halogens. And this is a group that we will work a lot with. The halogens are incredibly reactive. They are the most reactive of the nonmetals. And if anybody here is lucky enough to go on to take organic chemistry at the college level, you will do about 4 gazillion bromination and chlorination reactions. because the halogens are so delightfully reactive, and they tend to react strongly with biological molecules. They tend to respond, oh, they react with anything, but organic molecules take up chlorine and bromine very easily. The fact that biological things take up chlorine is why we can use chlorine to kill bacteria, because it interferes with the biological molecules in their little cells. So we do a lab typically in this chapter about reactivity of halogens, and you should know that if I'm saying the word halogens, I'm referring to group 17. That's something you just need to know. Sometimes these are, you'll see the term halide, and that's typically salt compounds with any other metal. You know, like sodium chloride is a halide. It's a halogen compound. You know, halides are halogen ions, and that name gets extended to their compounds. So the P-block is fairly important. Okay, so the D-block is that sunken area in the middle of the short form periodic table. This is where the stuff that you think of as metals exists. Your iron and your copper and your manganese, your chrome, those things are out here in the middle. They're called transition metals, and you can think about it as they provide a transition from one side of the periodic table to the other, or however you choose to remember it. This is where things get funky with the filling order, because this is where you start to, oh, let's see, we fill 4s2, then we fill the 3ds. You know, we fill 5s2, then we fill 4d. So we start to have those overlaps. The sum of the outer s and the d electrons is your group number. Now notice that that does not say number of electrons on highest occupied level. Why not? The answer, my friend, is written on the slide. The answer is written on the slide.
So would it be like
yeah, their electrons that behave like valence electrons aren't all on their highest occupied main energy level. Those d electrons, you know, if we have a 4s2 3d3, these are not on the highest main energy level. They're one level down. The weird thing is, in the transition metals, these things kind of behave like valence electrons. So the number of the outer s and d electrons is equal to the group number. What group is that in? 5. Yeah, that's a group 5 element. And actually that's vanadium. Or I'm sorry, yeah, group 5. Group 5, period 4. If I tell you that this is 5s2, 4d6, what group am I in? Yep, this is group 8. And this is actually, let's see, 5th period, and then 1, 2, 3, 4, 5, 6. This is Rutherfordium, RU, number 44. The reason it's important to know that, so in the D block, because it doesn't have the same kind of valence electron setup that everybody else does, where it's just the highest main occupied energy level, these Ds kind of act like they are valence. One of the things that very often happens is, see the Ds and the S's here, 4s is lower energy than 3d, but it's pretty darn close. It's like, if we go back to the dorm floors analogy, there's like one step in between these two floors. So sometimes you'll have some of these s electrons will actually migrate up into the d levels, and you'll have things that have what seems like it shouldn't be possible, a 4s1 3d4. I don't expect you to know that. Where that's going to come up is when we start doing a lot of compounds with metals, you'll understand better why the transition metals very often form more than one kind of ion. So iron, for instance, forms an iron 2 ion and an iron 3 ion. We'll get more into that later. We call this delocalization. The electrons are delocalized. They're not married to one orbital. They're not married to one subshell. They kind of end up moving around a little bit, which actually ends up accounting for some of iron or some of metal, transition metals' properties. The fact that those electrons are delocalized. Okay, now on to the big, the bad, the dangerous. Okay, so we'll finish talking about the D-block real briefly. They're often called the transition metals. These are the things that look and act and sound and feel like what you think of when I say metal. They're hard, they're strong, they're, good conductors, they're shiny, all that stuff, all the things you think of as a metal. They're not all that reactive. Many of them will react slowly over time, like iron, for instance. Will iron react with things? Sure. It reacts with oxygen in the atmosphere and rusts, for one. But a lot of them actually are unreactive enough that they don't even form compounds in nature. Anything that you can find as flakes of a pure metal out in the world is pretty darn unreactive. Can you think of anything that is found that way? Gold. Yeah, panning for gold. There was even a reality TV show at one point where people were panning for gold. Yeah, it doesn't form compounds in nature. It's just laying around out there. Some metals aren't like that. Iron, for instance, comes out of the ground in the form of iron ore, and it has to be purified before you have pure iron. So it does form compounds. Some of these things are unreactive enough that you can stick them inside the human body, and they don't react with all the chemical processes going on in there. So gold used to be the standard for fillings. That's been a long, long time before your time, before my time. Now they use like a plasticky stuff, most dentists. Titanium is another one that used to be used a lot in the body. I knew somebody who had the bottom of his leg crushed in an industrial press, like there was no bone between the knee and the ankle. Like it was just blah, 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 like a rubber chicken. And yeah, they put a titanium rod in, and that's able to stay inside the body. And he was told at that time he would have it for life, but he didn't. But that's another story. Gold is typically used. I worked with a woman whose father had an aortal aneurysm. So the aorta is the big vessel that goes, let's see, the aorta is inflow. I don't teach anatomy and physiology. Okay, you don't know that yet. So anyway, no, the aorta is an artery. It's under pressure. It's outflow. It's being pumped out actively. So it's under a lot of pressure. It's got a pump behind it. And the wall of the aorta can balloon out and get very thin, like a bulge in a tire. That's an aneurysm. Well, if your aortal aneurysm splits open, the survival time is typically counted in tenths of seconds, because your heart just keeps pumping all your blood into your body cavity, and you die pretty fast. So her father had an aortal aneurysm, and what they can do now is they take this, it's like mesh reinforcing wire, it's like a little mesh sleeve, and they stick it down in the aorta, and they pull that balloon up against the mesh. And so her joke was always, yep, my dad's got a heart of gold, because the mesh was made out of gold. And it has to be unreactive enough to sit there in the bloodstream and be exposed to all the chemicals in human blood and not react, not form compounds, not break down, not get weak. So these are the transition metals, are the things that get used in the body. Okay, so now we're talking about the Fblock. These are the big, bad, ugly, and dangerous. The lanthanide series is the top line of the Fblock, and they're not quite as big and bad and ugly. They're pretty reactive. They're about as reactive as group 1 elements, and we're going to see some reactions with group 1 elements today. A few of them are radioactive, but for the most part, they're just very reactive. The actinide series, the bottom row, these are all radioactive, every single one of them. Americium, plutonium, uranium. These are some big ones. So you don't need to know a whole lot about these. They're filling f orbitals. And they're filling 4 and 5 f orbitals. Now, what is the bottom period on the periodic table? 7, right? And if we tuck these in, if we do the long view, so if we do the long view and we look at these are filling in the 4f, because this was 6s, and remember the f block is always 2 behind. These guys are filling in the 5f, because remember this is filling 7s, and f is always 2 behind. This gives a whole new perspective to why you don't need to draw out all of the orbitals possible here. You really don't need to go beyond the line that concludes with 5s, because, you know, now while I said this is all of the, let's see, 5s, 5p, 5d, 5f, 6p, 6d, 6f, 7s, 7p. Yeah, that's as far as we need to go. What's the largest element that you've got on this periodic table? It's the atomic number of the largest element. 118. So remember I said when I gave you this that I was giving you everything in the universe? Well, we don't really know that. I mean, there could be scientists on the other side of the observable universe, 14.5 billion light years away from us, who have all of the elements we have and more. Now we assume that because this is science and this is what we're basing everything on, the rules work the same way every place. If you look on the back at the long view periodic table you've got, notice that there are gaps at 113, 115, and 117. So the things that are really big, the 118s and 117s of the world, they tend to be very, very unstable. They tend to have very short half-lives. Some of those elements, like 113 and 115, literally have half-lives in seconds. So if you create a sample of element 115, by the time you're done measuring it, it's gone. They're just not stable. They decay. They decay into other elements. There's no way to know if there are scientists on the other side of the universe doing work with elements that we don't know about yet. We would assume that the physical laws that govern how atoms go together and stay together are the same, but we really just don't know. Okay? So, could there be things that are filling the 7D and the 7F and the 6F? There could. Not that we know about. So, for chemistry here on Earth, with the elements that we are aware of, we don't actually have anything that will fill up into the 6F and 7F, because the F block is just filling the 4 and 5F. Okay, so this is the first half for 1118 period 6. We'll pick up with the second half in another video.